D'accord.
I'm Dr. Leonard Hazan from Camden County College, and today's lab deals with properties of optical fibers. We will consider 4 experiments in this lab. The first one will measure the numerical aperture of an optical fiber. The second experiment will measure the attenuation coefficient of light in that fiber. Then we will construct a fiber optic coupler, so we will be able to split light to different fibers. And finally, we will check the wavelength division multiplexing, combining several different wavelengths in one fiber. These will be our experiments. As you know, optical fibers have revolutionized optical communication, and here, I don't know whether you can see, is an actual multi-mode telecommunication fiber that is used to transmit data, voice, and video. And this single fiber can transmit up to several million, for instance, telephone communications, which is can replace hundreds, even thousands of former used electrical copper cables. And the first thing, we will measure the numerical aperture of this fiber, and I will first tell you what it is about. As you understand, as you know, light is reflected along this fiber because of total internal reflection. Here you see a light go straight, but if I will incline this laser pointer, you see how the light bounces up. But it only will occur if the angle is larger than the critical angle. So if my angle is smaller, the beam will not be bounced, it will escape from the fiber. Here I have the corresponding drawing, and this angle theta, the maximum angle theta that our light still will be channeled inside the fiber, is called an acceptance angle. And sine of this angle is called numerical aperture of the optical fiber, and our first experiment will deal with to measure this numerical aperture. Let's go to the slide showing the procedure for the numerical aperture measurement. First, you cut off a segment of a fiber, for instance, a 1 meter segment, paying special attention that the both ends are straight. Then you assemble the light source, the fiber, and the white paper screen according to the next slide figure, which I will show you shortly, keeping the distance of the fiber from the screen about 30 centimeters. Shine the light into the fiber, and on the screen draw a circle outlining the light spot. Measure the diameter of this spot in centimeters with a ruler. Use the equation to calculate the numerical aperture. As you see, numerical aperture is the sine of the inverse tangent of the ratio, the diameter of the spot, over the doubled distance of the fiber from the screen. Now let's go to the figure 440, that shows all this assembly. You can see a laser illuminating that fiber. You see the distance z of the fiber from the screen. You see the spot on the screen with its diameter d, and you see that the acceptance angle theta a, and you see that the tangent of this angle is equal the radius of the spot over z. That agrees with the formula presented on the previous one. So we will use a light source. For instance, it can be used a laser pointer. Then we use optical fiber. We can, of course, use this real multi-mode optical fiber, and you see what spot it will produce here. And we can measure the diameter of this spot. We can measure the distance of this fiber from the screen, and we can measure the sine of this angle. I want to emphasize here that because the diameter of the core of the fiber is much larger than the wavelength of light, the diffraction spreading is negligible here. So here in this experiment, light travels according to geometrical optics along straight lines, and that is why this experiment really gives you numerical aperture. And now you see the data table 1 for the numerical aperture of an optical fiber. So enter the distance to the screen Z and the spot diameter to the corresponding columns and the calculated numerical aperture to the last one. Our second experiment is a measurement of an attenuation coefficient of an optical fiber, and the attenuation coefficient is measured in units that are called decibels. So you can see a figure that shows you the assembly for measurement of attenuation in fiber. You see a light source. It can be a laser sending light over the coil fiber of a long length L. The other end is connected to the photo detector, and the power meter reads the power. After the power is read from the long fiber, you cut the coil out, leaving about 1 meter of the fiber attached to the laser, and measure the power again from that piece. And now let's go over the procedure for attenuation measurement. As I said, you cut the length of the fiber about 1 kilometer or several hundred meters. One end attached is to the light source, and you measure the power at the output end of the fiber. Without disturbing the coupling of the fiber to the laser, you cut off a 1 meter reference length of the fiber from the input end, and then measure the power Pi of exiting light. This will be the input power to the longer fiber. And then you calculate the attenuation coefficient alpha in decibel per kilometer according to the following equation. It's 10 common logarithms, power sub I over power from the long piece of fiber, and that log is divided by the long length of the fiber in kilometers. And then enter your results in the table 2, as you can see it on the next slide. The next experiment, we will make an optical coupler. For that purpose, we will use plastic fiber. Our plastic fiber doesn't have a jacket. This glass fiber has a jacket coating here, which has to be stripped to make a coupler. But our plastic fiber doesn't have a jacket, so you can simply twist it, for instance, and then heat with a heat gun, and it will be melted together in some point. And you will have, as you see on the slide, you can see this fiber coupler. And then when in one port of this this fiber you will send light, you can measure power exiting from both ports, port 2 and port 3, and see how light sent into the port number 1 is spread over ports 2 and 3 of 2 coupled fibers. Finally, the final experiment, we will demonstrate wavelength division multiplexing, and this is a currently used technique to squeeze many channels to a single fiber. All communication channels, they have slightly different wavelengths, and they are combined in one fiber, and then at different points of destination, different wavelengths are extracted. So we will use our coupler. We will use 2 ports, and we will use a green light and a red light to one port of this coupler, and then you will see how these 2 lights are combined and compound in outgoing output of the coupler. So you see that that outgoing fiber really channels 2 wavelengths, and to see that we will use a diffraction grating to separate them back and see that really that outgoing fiber had 2 different wavelengths. So then I show you the actual setup.